Hi everyone, thank you for coming. Today we're going to talk about how adversaries bypass and beat user mode solutions. As I was presented, my name is Omri. I'm currently an independent researcher doing mostly low-level research around OS internals and malware. I've spoken at a few conferences before, but it's my first time here at VB. So our agenda for today will give you a basic introduction to the subject, go over some basic terms, and we'll cover the three major tactics that attackers use to beat user mode based protection engines, and cover some conclusions at the end. So what is a user mode protection engine? Basically, it's this component that is injected into user mode processes. User mode monitoring is possible in two ways, either instrumentation, that basically means that the software package is already being modified by the software provider to provide the vendors with some capabilities, or monitoring can be done in user space via hooking. That is done on runtime by the vendors themselves. Why do that in user mode? Writing code in user mode is considered more stable, won't cause any blue screens, more simple to develop. There is no patch protection in the user space, unlike in the kernel on Windows. And also, you got the full context in the user space. For instance, if you have an application that uses SSL or TLS sockets as example, so the data will only be in clear text at the user space. There are a few options to perform hooking. The most common one is called inline hooking, which basically means that the target function we want to monitor will go directly into its instructions in memory, and we're going to override them, usually with control flow instructions. And it's the most common hooking method right now used by security products and solutions. You have a few examples listed here. So the first tactic that we're going to cover is basically hook evasion. All the content in the slides is not sorted in chronological order. Okay, so it's important to note. And also, I included references to all of the sources that you can see in square brackets along the slides, and there is a list at the end of the slide that you can refer to. So how can an adversary evade the hook? Basically, if the hook overwrites the original instructions, the attacker needs to find a way to execute them and then continue to the rest of the instructions. In this tactic, there are four groups of techniques that we are going to drill down into each of them right now. The first class is called secondary DLL mapping. It's quite self-explanatory. The malware will try to create its own private instance of the library that it won't basically be detected by the protection engine, and it will have the code, the original code there, and so it can use that instead for the rest of its operation. There are three techniques that can be done to achieve it, whether it's use reflective loading, clone the DLL on disk, copy it on disk, and reload it again with a new name, or remap the section using low-level NT APIs. So these techniques can be detected. I've listed some indicators here, and also some of their drawbacks. Basically, if you analyze in runtime, if you analyze the call stack, which part of the code that participated in a specific operation, you'll see certain differences. Either you'll see missing relevant DLLs in the stack, or DLLs that you didn't expect to see there, and those are identical to other system DLLs and stuff like that. During forensics work, if you capture a snapshot of the process, you can also pick up on this technique, on this class of techniques, as you can see here. You can go over and find floating PEs in memory, or go over the PEB and correlate for duplicates and things like that. The next class that we're going to cover is called binary restoration, or in a more simple naming is simply unhooking. Just remove the hook. Once the library is loaded, and the protection engine then installs the hook on certain areas and certain functions, basically we have to find a way to restore the original code. There are 4 different techniques to do that. The first one, that if you listen to the previous class, is basically utilize that, because the secondary DLL mapping already gives us the original code. So we can just copy the code from there and restore it back to the original DLL in memory. Or if we don't want to access the file directly ourselves, we can use other processes and basically get the code from their memory space. There are 3 variants to be able to do that. Attacker can create a suspended child process, but that will only give them a specific DLL, only the anti-DLL. They can create a debug DLL and then wait for the target DLL that they want to obtain the code for it to load. Or they can just search in existing processes, because not all processes are being monitored. So they can just look up there and iterate the running processes, look it up there, and read the process memory, and again, restore the code with virtual protect and memcopy. The third technique here is called section refresh. Basically, instead of getting to disk, getting the code from disk and rewriting it, or using other processes to get the code and rewriting it then, we can just capture the state of the data sections and then remove the mapping of the code in memory with the low-level APIs. We need to obtain a handle to the section for this, then unmap the code from memory and map it again at the same address it was. And then restore all the data sections and state of the DLL. The last technique is called short-circuiting. Basically, we can, instead of, an adversary can, instead of either overriding the code or getting the original code from disk or doing a lot of very complicated things like that, you can just find the original code that the hook engine, the protection engine, copied elsewhere, because if you think about it, the protection engine also needs the original instructions in order to operate correctly. So you can just search for it, scan the process address space for it, specific memory attributes, and then for the control flow instruction that leads back to the hook itself. And once we found it, we can do 2 things, one of 2 things. We can either overwrite the hook itself in place directly to the original code, to the original stub, sorry, or we can override the trampoline, which is usually an area, an intermediate area that is used by the hooking engine for a variety of reasons. So how can we detect this class of techniques? We can see that during forensic, it will be quite easy to detect this. There's also a volatility plugin that I referenced for it that tries to do just that. It was released last year. And we can see that for runtime indicators, we have a bit less opportunities here, but it's still somewhat possible for some of those techniques. So the next class we're going to discuss is regarding direct system call. The main issue with all of the previous techniques is that they are dependent on system calls. So defenders can still hook them, and by having them monitored, prevent all the previous methods. So to overcome this, attackers directly call the system calls themselves, not needing to go through any hook whatsoever. To understand this, we need to look at the internal structure of the interface of the system call. Basically, what's important to note is that the index that represents the system service is being placed at the EAX register, and then either the syscall instruction is used, or the int2e. Now, what's interesting is the int2e was the old interface to transition to the kernel, but with VBS, virtual-based security on Windows, it was brought back and it's reused again. And now it's again the default method the OS uses. So the first method here attackers use here is basically to manually pass the instructions of NTDLL and extract the system call index. You can do that from disk or from memory, as we discussed before. It's quite simple, and then they get the index and directly use the syscall instruction. There are two other techniques that can be done without parsing, without using disassembly or pattern matching. If we look at the characteristics of NTDLL, we can see that the exported NT functions are basically appears in memory one after the other and sorted according to the index. The offset that you see to the left of the functions is not there by accident. This is how they are placed in the file and in memory itself. So you can either count till you get to the function you want. You can create a sorted list and count till the function you want. Or you can just go directly to the function you want to use. And if it is hooked, you can go to its neighbor and try to parse the index directly from it, and then add or subtract depending on the direction you took. The second method here is Evans Gate. It's a specific case on Windows that basically allows 32-bit applications to interact with 64-bit applications using basically the emulation layer directly within the malware itself and skipping the OS DLLs. So there are two variants that can be used here. If you can see, we hooked, for instance, the 32-bit function. So basically, you can skip as I mentioned, you can skip the WO64 emulation layer and go directly to the native NTDLL that is in the process once you transition the context to the 64-bit inside your 32-bit process. Or you can use any other method that we discuss to parse the NTDLL index, and then just directly call syscall yourself. The third method here for direct system call invocation is basically by parsing the kernel itself. We don't have to parse NTDLL. If you think about it, the same index that is in NTDLL has to be in the kernel binary as well. So we can do that, and we do that in user space. We don't have to have any kernel readability. We just load up the kernel binary and read it into user space. And then we need to look for the ZW functions, because in the kernel binary, those are the functions that hold the index. But not all system calls have, not all the system service has the ZW function exported. So for some, you only have the NT variant exported, but the same table, the same values, all of the indexes have to still be in the kernel. So they are found in a private and non-exported structure that's called the KI service table. And it's possible to locate it if we take a few pairs of ZW and NT functions that are exported. And then we only have to take the NT function that is exported once we found it and traverse the table and to figure out the index itself. While this method is not the most, it doesn't correlate to all system services, it does provide with the malware developer for most of the functionality it needs, as you can see listed here. The next method is basically, doesn't rely on any parsing whatsoever. Basically, attackers bring their own index with them, whether it's hard-coded in the malware binary or in some configuration files or whatever. But this means that for every OS version that they want to support, they have to know the specific index, because the system call service index is not guaranteed to be the same with each Windows build. The last technique here is called dynamic resolution. Instead of doing a lot of parsing, complicated parsing, or relying on having everything hard-coded beforehand, you can just try to resolve the index on runtime. Basically, using exception handler and placing a hardware breakpoint on the syscall instruction of the system call service that we want to use, and then trigger the function and wait for the breakpoint to trigger. And once we have that, we can extract the index value from the EAX register in the exception handler itself. And we can let the function continue and finish, or can just kill it off. But at that point, we already have the index. So for the detection of these techniques, it's quite easy to understand that we'll be missing very critical system DLLs in the process. So in runtime, it will be quite easy to pick it up if we look at the call stacks. And in forensics, we don't have a lot to work with because all the code can be obfuscated or packed. So at the time of forensic, the instructions that the syscall instruction, for instance, might not be visible. So it's hard to scan for it. Even though the volatility plugin I mentioned tries to do that. I don't know how good it is. I didn't try it out. And the last thing here, also regarding the runtime indicators, as I mentioned before, a lot of the implementations don't use the syscall instructions, even though that's not the default instruction that the OS uses. So if we look at the call stack and we see that the syscall instruction was used instead of the int2e on Windows with VBS enabled, that might also serve as an indicator at runtime. The last class here on the hook evasion tactic is called code splicing. Basically means that you're going to rebuild the functions tab at a different location. In the past, it was used by packers and anti-cheat solutions. Basically, we use the reflective loading to get the code, and then just create a different prolog copy in memory. And from there, each function call will go through the prolog and skip the hook if it's ever installed. The last technique is called stub reuse. As we mentioned before, it's possible to find the original stubs, the original function instructions. So why go through all the trouble? We can just call directly to it. And that will be quite simple to achieve. If we try to examine it from a detection perspective, so for code splicing, we won't have any real indicators, not for runtime, nor for forensics. But it still has some issues because the internal functions can still be hooked because we don't remove any hook whatsoever in this scenario. All right. So we finished with the major part of the session. Now we're going to cover two newer tactics that are being used. We start with argument forgery. For it, basically the concept is different. Right now, if attacker tries to evade the hook, here the attacker won't try to evade the hook, he'll just go through it. But it will give the protection engine false values, so the detection logic won't pick up on its operation. But later on, they will swap them for the real malicious values. So this is basically a time of check, time of use issue, which is a popular, very well-known vulnerability type. To do that, to achieve it, basically there are two options. Either leverage hardware breakpoints again. It is very similar to our dynamic resolution, to the dynamic resolution technique. And there is another method, but it's not as reliable because it depends on the specific vendor code. Basically, to feed the protection engine an argument that will cause it to generate an exception and then switch the parameters at a later point. So how it is implemented, if we look at the hardware breakpoints method, which is the reliable one, basically, after we set an exception handler, we try to understand as an attacker where the protection engine is going to return to. I put on the screen the hooked and original function instructions one next to the other. And if we can see that at the +7 offset of the function is where the return and the original instructions continue. So once we look at that, we put a breakpoint, we define the breakpoint on it, call the function with fake parameters, and let the function run. At a certain point, we can see that the protection engine will go back to the +7 offset of the function. Then the breakpoint will hit, we'll swap the parameters for the malicious one. For example, here it's for the URL. Either we'll swap the parameters depending on the function's calling convention, either the registers on the context structure or the parameter values on the stack. And as I mentioned, the malicious URL, and continue execution. All right. So the last tactic here that attacker use is called engine disarming. If we try to disable the hook, evade the hook, or go through it, right now the attackers will go through a different approach. Why not just disable the entire engine in user space, the entire DLL that is loaded into the process? They can do that by either calling free library, or trigger the engine's specific unload function. Some vendors do support it for uninstall purposes. They can try to unmap all the DLLs on the process, but that will leave them in a bit of an issue because they won't have any functionality left to use. They can try to leverage the OS process mitigations to allow only Microsoft-signed binaries to run, but that will mean that their payload can be a DLL, only an executable, so it has some limitations. Or to preload in a new process when you run a new process and prevent the protection engine from loading inside of it. It can be done, again, using the debugger APIs or by injecting into the process at an early enough stage and run before the protection engine even loads there. There are also other vendor-specific issues that I won't cover. Just as an example and a reference, to toggle the hook enable disable flag in memory, as some have done. So I have a couple of more slides, just the conclusion and the reference, and then we'll get to questions if you have any. So everything we talked about is quite trivial to implement, quite easy to use. Most of it have source code online if you want to experiment with it. If I sounded repetitive during the talk, you didn't imagine it. A lot of these techniques are sharing the same primitives and concepts, and just reuse them in a slightly different way. This is the probably most prolific post-exploit technique that even overcomes, even surpasses code injections. I also included some statistics from the last 5 years or so, so you can see how much have changed. If you thought about why I didn't mention MITRE ATT&CK so far, so the content you have in the attack framework regarding this is very, very minimal. It only mentions in a single paragraph this entire topic and only reference the unhooking or engine disarming portions of it. It's also this evasion technique is also prerequisite for other evasions, basically because they also require first to run code, to have code executed first, such bypasses such as ETW and the AMSI bypasses. The last and finally, a lot of the detections that I talked about were regarding call stacks. There's also an ability, attackers also develop some ability to spoof the call stacks in order to evade detection, but that can be also mitigated if you leverage CET shadow stacks or if you build an emulator or a sandbox and you control the hardware. You can also implement transition-based code tracing, as some have done. 2 final points. I mentioned that user mode code can't cause blue screens. I kind of a bit lied. If you have a critical process, it can create a blue screen as well. And finally, using user mode hooks for security is just not enough. It has a very big design flaw that it relies on the same environment it tries to protect. And I'm also releasing a white paper that will be available on the VB website. It has more details on a lot of more malware families, reference to open source projects, and details on detections. This is the time for questions if you have any. I'm just putting the reference slides if you want to take a screenshot. The slides will also be published in the VB website.